Okay, so this is our last podcast of Unit 7. We're going to be talking about a special type of reaction called redox reactions. And redox just stands for the words reduction and oxidation. These are two things that are happening in all redox reactions. So we're going to learn a lot more about these reactions and what those words reduction and oxidation mean. This is going to be filling out pages 16 and 17 in your packet. We're going to do all of it. I'll leave a couple of problems for you, but not much. So let's get going. So redox reactions. These reactions, or also known as oxidation reduction reactions, or flip it and reduction oxidation, involve reactions that have a transfer of electrons between two different chemicals. So all these reactions are happening because the atoms are moving around. These special reactions, redox reactions, happen when the electrons are being transferred between these atoms. Now, the oxidation numbers, also known as the charges for the most part, must be, take away the must be all. Oxidation numbers of the elements will be used. So we're going to talk a lot more about oxidation numbers in just a second and how to find them. For the most part, they're the same as charges, but not always. So we need to get used to this new word, oxidation numbers. Now, a redox reaction has occurred when an element undergoes a change in their oxidation number. And that comes back to that transfer of electrons. If an atom gains or loses electrons, then their oxidation number, aka their charge, their effective charge, is going to be changing. It kind of makes sense. So let's first dig into how oxidation numbers are sometimes the same and different than our charges. So we have this table right underneath that intro, and this kind of helps us see the difference. First off, single elements. Either if it's an uncombined element like sodium, or even a diatomic like oxygen, O2, if it doesn't have a charge written on it, then it doesn't have an oxidation number. Its oxidation number is 0. On the other hand, if I have something like this copper here that has a charge written on it, copper plus 2, then the oxidation number is equal to the charge. So those are the easiest ones, is the single elements, things that aren't in a compound. They either have a charge that's equal to their oxidation number, or they don't have a charge and they have a 0 oxidation number. Now, for the rest of our compounds, we're going to have to try and figure out these oxidation numbers based on a couple of known elements. And our known elements that we can rely on to always have the same oxidation number are oxygen, hydrogen. I actually want you to add in fluorine there. You might not have a space to add that right there. I think you have some words right underneath your table, so you might end up writing it like over here or something. But make sure that you write this down, because fluorine is always going to have a -1 charge. It's the most electronegative element on the periodic table. When there's a battle over who gets these electrons and who gets to have that negative charge, fluorine is always going to win. So we need to remember fluorine. Our other two elements, oxygen, does always have a -2 charge. I know it says in peroxides it won't, but let's go ahead and scratch that out, because those are literally the only two peroxides you're ever going to see, the sodium peroxide and hydrogen peroxide. And you're honestly never going to see them after the practice problems that are right below this table, because they're just so weird. I don't want you looking for that peroxide, that O2 group, and being like, oh, that's carbon peroxide. It's not. That's carbon dioxide. It's completely different. So I just don't really believe in peroxides. They don't exist other than these two. So there's just too special for our chemistry level that we're at right now. So fluorine's always -1. Oxygen is always going to be -2, and then hydrogen can be either a +1 or a -1. Most of the time, it's going to be that +1, just like everything else in its column is a +1. But if it's with a metal, the metal is actually going to be the one that it gets to be positive. So in that case, hydrogen can be negative, but for the most part, it's going to be +1. We're not going to see these metal hydrides very often. These are pretty rare, but they do happen. So if you're out and about and you see something like that and you're like, but that can't happen, they're both positive. Well, hydrogen can be negative, but rarely. So these are the kind of general rules, but really what we're going to do is a lot like when we were trying to find the charges of the transition metals, is start by looking at the part of the compound that we know, the end part, and then work to the beginning. So we're going to do some of these practice problems down here together, and it all comes back to balancing their charge. This is that part that's right underneath your table, the words. In a neutral compound, in a compound that doesn't have a charge written on it, like these, the total charge is going to add up to 0. In a polyatomic ion, like ammonium and sulfate, then the charge, or the oxidation numbers, are going to add up to whatever this charge is. So in ammonium, it's going to add up to that +1. In sulfate, it's going to add up to -2. So we're still kind of doing that same idea that we did before, just adding in the fact that not all of our elements are going to follow the right rules. So let's look at these. So first, oxygen. This is just a single element, and I don't see a charge written on here, so our oxidation number is 0. A single element, nothing to hide. If you don't see it, it's not there. Over here, on the other hand, we have calcium, just kind of skipping ahead. It has a +2 charge written on it, so it has a +2 oxidation number. Right next to that is normal calcium. No charge, 0 oxidation number. So, a couple of simple elements there just to get us started off. You might see some more elements in that mix, and you might be able to mark their oxidation numbers. Now, let's move on to this ammonium. So, we're always going to start from the end, and that H gets a +1 oxidation number. We're just going to go with that. Hydrogen gets that +1. And now we have to kind of balance things out. And actually, I just wanted to get this little scale to appear real quick, because this is what we're doing. And I'm not going to do this for every single one, but I have 1 nitrogen and 3 hydrogens in this compound. This is what we should be visualizing. In order to figure out what nitrogen's oxidation number is, we have to start from that hydrogen, that part that we know. Each of those has a +1, so I have a total of a +3 here. And if our total has to add up to 0, then that nitrogen has to be a -3 for its oxidation number. So this is the balancing act we should be doing in our head. In our next example, this is actually an ionic compound with a transition metal in it. So we've done this type of thing several times before. I have 2 chlorines and 1 copper. And if I start from the chlorine is the dependable part. It's going to have a -1 charge, a -1 oxidation number, which means our total negative is -2. Which must mean that our positive, in order for this to add up to 0, must be +2. So this is copper 2 chloride, because it has a +2 charge, a +2 oxidation number. So all of this stuff has been pretty normal. We have this ammonium, which starts to shake things up a little bit, mostly because in here, when we have that 1 nitrogen and those 4 hydrogens, our total is going to add up to a +1 because of that positive charge there. So if I think about it, and I have my 4 hydrogens, which are going to have a +1 charge, which gives us a total of a +4 in this compound, what does nitrogen's charge, what does its oxidation number have to be to add up to +1? So something +4 gives me +1. Well, that's going to be -3. So here, our hydrogen has that +1 oxidation, nitrogen has a -3. Honestly, all of these oxidation numbers we've found so far are basically the same as the charges that these elements can and normally have according to the periodic table. This next example is going to break all of that. So what I want you to notice here is that this is a covalent compound. So technically these aren't charges. These are oxidation numbers, like we've been saying. They've just been kind of interchangeable with our normal charges. So here I have 1 N and 2 O's. If we start from the oxygen that we always, no matter what, is going to be -2 for its oxidation number, that gives us a total of -4. This compound does not have a charge written on it, so its total has to add up to 0. And, I did that backwards. careful about those subscripts. N2O means I have two N's and one O. So that means I have a total of a -2 charge, which must mean to add up to 0, I have to have a total +2 charge. But I have two nitrogens there, so that's going to get split between them. And each of those nitrogens is going to have a +1 oxidation number. So this is completely different than all the other nitrogens that we've seen on these practices so far, and completely different from what the periodic table tells us to expect. So let me reiterate, this is not a charge. Nitrogen here does not have a charge. What this tells us is the relative attraction for electrons. So this is just saying oxygen is going to be hogging all the electrons way more than nitrogen is in this compound. And that makes sense. It's more electronegative, so it's going to get to steal them. And poor nitrogen doesn't really like having this +1 charge, but it does it. So this is an oxidation number. +1, -2. Now, in our next example, chloride ion, this is just chlorine. And when it is an ion, it has a charge of -1, which means its oxidation number is -1. So those are all the examples that I really want to do. I'll do one more. So first, cross this one out. I'm going to have you do a couple of them in a second, but don't do that one. Let's do sulfate. So here, let's start from the oxygen. It has a -2 oxidation number. I'm going to set up my table. So here I have my 4 oxygens that each have that -2 oxidation number. And so I have a total -8 oxidation number over there on the oxygen side of things. Sulfate itself has a -2 charge, so that means that something plus -8 is going to get me -2. And that something is going to have to be a +6. So this sulfur has a +6 oxidation number. Completely different, once again, from what the periodic table would lead us to believe. Now, right next to it is calcium sulfate. And so this compound does add up to 0 charge. I don't see any charges on here, but technically between these pieces, I know calcium's going to be a +2, and just like what we saw before, this sulfate overall has a -2 charge. So if you do see an ionic compound that has one of these polyatomics in it, you kind of have to treat it by itself and find out what it adds up to individually, and then balance that with the other ions. So just like the other sulfate we just saw, that sulfur is going to have a +6 and oxygen is a -2. So these are all the examples that I'm going to do. I left a couple for you. Some of them are simple, some of them are not so simple, but I want you to try them. I'm not going to base your stamp on this page off of these couple of examples, but you might see these in your bell ringer, so go ahead, try them out. We're going to move on and start talking about what oxidation and reduction really mean when it comes to these oxidation numbers. So if you notice, I've broken this across 2 pages because there's actually 2 different sayings that relate oxidation and reduction. So what I wanted to point out here is how they go together. So in the first column is oil rig, and in the second column is Leo Gur, or the saying that you might remember is Leo the lion says Gur. Both of these are going to get you the same kind of information, and you can choose which one is more helpful to you to remember what oxidation and reduction are. So, if an element has lost electrons, and thinking about it, that means that their charge, their oxidation number is going to be increasing because they have less electrons, less negativity, so it's going to get bigger, then that has been oxidized. Oxidation has happened. And the way that these sayings are going to help us, oil, part of oil rig, stands for oxidation is losing. But sometimes that one's a little bit, it tells us very specifically, oxidation is losing, but losing what? And so I like Leo the lion says Gur, because even though it's a little bit longer of a saying, it's more specific. The Leo part says losing electrons is oxidation. So, you see, it tells you the same information, but the oil rig one, you have to remember what you're losing. Don't think you're losing charge, that your oxidation number is going down. You're losing electrons. So, that's oxidation. And then, if an element has gained electrons, the opposite, that means that their oxidation number has decreased, gone down, because I have more electrons, more negativity in that atom. then we say that it's been reduced. That kind of makes sense. Notice, decreasing the oxidation number is reduction. Going down is reduction. So that can kind of help you on its own. And then the rig part of oil rig tells us reduction is gaining. And the gur part of Leo, the lion says gur, is gaining electrons is reduction. So either remember oil rig, oxidation is losing, reduction is gaining, or Leo the lion says gur, losing electrons is oxidation, gaining electrons is reduction. Your choice. Or come up with something on your own or find something else. I'd love new tricks to remember this stuff. So that's the basics, and this is how you're going to be kind of quizzed and tested over this, is we're going to give you a reaction, and we're going to go way farther into this next class together. But we're going to be looking at some half reactions. So don't worry about like the chlorine in here. Like, oh, where'd the chlorine go? It's not balanced. This is impossible. This is just half of the reaction technically. But what we're going to do is look at how the oxidation numbers change for a given element. In this first reaction, we're just going to look at copper. And here, copper is starting from a 0 because it's just a lone element on its own. And then if we look at that compound that it's going to be in, we already saw that on the other side, that copper gets a +2 charge. So here copper's oxidation number is going from a 0 to a +2. That means the charge, the oxidation number is going up, which must mean it was losing electrons, and that means that copper has been oxidized. Oxidation has happened to copper. Now, in our second example, the silver started off in a compound, then with a +1 charge, and it ended as a single element with 0 charge. So it went from a +1 to a 0. The oxidation number, the charge, went down. It was reduced. So we're going to be looking at these reactions and telling whether something has been oxidized or reduced. So in these next two examples, I went ahead and I marked our oxidation numbers just to save us a little time. When we have a full-on reaction, we need to look at how each individual element changes to figure out which one is being oxidized or reduced. So if I look at zinc before and after my reaction, so with zinc going from a 0 to a +2, its charge is going up, must be losing electrons, and oxidation is losing. So zinc is being oxidized. As I find my next copper is going from a +2 to a 0. Its charge, its oxidation number is going down, and so that's being reduced. If you noticed, our chlorine isn't changing. -1, -1. There's only ever going to be one thing being oxidized, one thing being reduced. Because as we talked about, oxidation is losing electrons and reduction is gaining. This is a pair of reactions. The oxidation that's losing electrons is giving them to the element that's being reduced. So you're always going to have one of each. These can't happen by themselves, and you're always going to have one element doing each of these. So looking at our next example, magnesium is going from 0 to +2. The charge is going up, so that's being oxidized, and oxygen is going from a 0 to a -2. Its oxidation number is going down, so it's being reduced. Oxygen's being reduced, not oxidized. So that is those two examples. In the next two examples, I've found all of your oxidation numbers for you, so I want you to give this a try. I'll check this as I'm coming around and stamping things, see if you can figure out who's being oxidized and who's being reduced. In this next example, though, I kind of want to go through because, aluminum's not changing, chlorine's not changing, sodium's not changing. Nothing is changing. Nothing is being oxidized or reduced. And that's because this is a double replacement reaction. This is not a redox reaction. Double replacement reactions are never going to be redox. They're never going to have a transfer of electrons. They're never going to have an oxidation number change. That's actually not too surprising because when we learned about these double replacement reactions, we said that charges do not change. So out of all of our types of reactions, the hardest ones to balance on their own are double replacement. And now these are going to be the easier ones because we don't have to do this redox stuff to them. So Go ahead, make sure you finish that example with the water there and those couple of oxidation numbers on the other page, because you might be seeing those again near the beginning of next period. And I also wanted to just give you an idea of what we're going to be doing with this on the test, because that's coming pretty quick. You need to know the definitions of redox, oxidation, reduction. You're going to have several questions just on what do these mean, like that oxidation is losing thing. You're going to have one question where you're asked to identify which element is being reduced or oxidized, just like these questions we're doing right here. Then a couple of questions that ask you to identify what is the oxidation number of a specific element in a compound, like what we did on that first page. 2 or 3 questions about that. And then 2 questions that are going to use this big complicated thing that we're doing next class period, where you're balancing using all of these skills plus a few more steps. So most of what we're doing with this is the stuff that you're learning in this podcast. And next class period might get a little scary, but you've done what you can to get these basics. So we'll work through it together, and hopefully it's not too bad.